Hello learners, in this video we are going to see about the mathematical model of brushless DC motor. So usually the mathematical model in the sense for a motor, which it is the combination of electrical, mechanical and relationship between the electromagnetic parameters also for that particular motor. So a common model, mathematical model for a brushless DC motor can be derived as here shown here. So first one, the electrical equations of the BLDC motor has been given here. So VA is the let us consider first the three-phase BLDC motor. So A, B, C are all individual phases, three-phase motor. For first phase VA, so we are writing the equation as RIA plus LDI by DIA by DT into EA. This is the voltage equation for the motor. So this represents the inductance of the coil inductance. Other parameters are shown here. That is, VA means VA, VB, VBC means phase voltages, and IA, IB, IC are the respective phase currents, three-phase currents. So R means the individual phase winding resistance. Okay, then L is the phase inductance, and EA, EB, EC is the back EMF. We know the back EMF. The back EMF is the important parameter which is very need in a motor to produce the torque, because as per Lenz's law, when we applied the voltage to a motor, it will produces the opposite reaction for the cause which producing it, so that the back EMF is produced likewise. So in matrix form, the equation can be written as like this: VA, VB, VC equal to R into IA, IB, IC plus L d by dt into IA, IB, IC plus back EMF components. So for a star connected motors, as it is a balanced circuit, we have neutral point in a star connected motor, so that all the phase currents will get meted up in the neutral point. So the IA, IB, IC summation of this algebraic sums equals to 0. So then back EMF equations. So each phase produces the back EMF equation with this equation KE FA theta WM, in which the KE depends on back EMF constant, and WM is the mechanical angular speed, whereas theta is the position of the rotor. Okay, these FA, FB, FC indicates the back EMF, trapezoidal back EMF waveforms. So for an ideal BLDC motor, these these waveforms are approximately trapezoidal, and we know that for each and every three-phase system there is a 120-degree electrical displacement is there. Okay, so the next one is electromagnetic torque component. The relationship is given here. So this is nothing but V into I concept only. Okay, so EIA plus EBIB plus ECIC. This means each and every three phases components are added up and divided by this angular velocity of the motor. So this is the moment of inertia J d omega n by dt for is equal to the T is electromagnetic torque produced and TL is load torque. So actually the torque produced from the armature does not completely given to the load side. It will get some of the losses, so that is actually the difference between this TE minus TL actually mentioned that only, minus beta omega m, that is viscous friction coefficient and mechanical angular velocity. So the rotor position can be indicated as d theta m by dt, which is equal to angular velocity. Okay, so electrical and mechanical relationship can be related through the poles, number of poles. So omega electrical angular velocity, okay, angular speed, and electrical rotor position, which that is W omega E, and theta E is the electrical rotor position, and omega E is the electrical angular speed. This is given by that P by 2 into omega m, and theta is rotor position is given by P by 2 theta m. Okay. So this is the complete BLDC mathematical model. This is for voltage, and this is for torque, and this is for electromagnetic torque relationships, and finally as